Hi.
We're now hearing a presentation from Joshua AULD. He's a computational transportation engineer working at Argonne National Laboratory, and will speak about work on transport modeling on HPC and with agent-based models. Thanks again, and if you want to say a few more words for introducing yourself before starting, please do that. And then just share the slides, and we should be able to see them. Thanks.
Sorry, everyone, for the technical difficulties. So as I said, I'll be presenting today on the modeling of future mobility impacts through our Polaris simulation tool. And I'd like to acknowledge the work of my colleagues, Mahmoud Javan Marty, Omer Verbas, Hassan Islam, Dominic Krapowski, and Emir Kerso in completing this effort. Next slide. Oh, sorry, one more slide. So the focus of our group is largely on addressing the transportation energy impacts of future mobility at multiple analysis levels. So historically, we have been a vehicle simulation group. So focusing on things like eco-driving, powertrain electrification, predictive control, and so on within a single vehicle. So really component design of vehicle systems. But we've been expanding that up to higher scales, including small area networks of connected vehicles and vehicle infrastructure issues. And then the new work is on expanding into modeling entire urban areas, which is the focus of the talk today. So really focusing on issues like travel behavior, network operations, ITS, platooning, connected automated vehicle systems, and so on. And that's all done through our Polaris transportation system modeling tool. Next slide. So why do we feel that modeling transportation system simulations is important in this field, and why it matters from an energy perspective is that new travel mode options may alter many aspects of transportation system simulations, including vehicle purchases, vehicle usage, and overall travel patterns. So we think things like shared mobility has a potential to decrease vehicle ownership, but possibly increasing the number of miles traveled and alter the way congestion patterns form and dissipate over large area networks. Also, at the same time, we have issues arising around electrified mobility. So as transitioning to BEVs and XEVs, we have the potential to see altered usage patterns, charging behavior, and infrastructure, which can influence, again, the issues relating to shared mobility. And a third leg of the issues we're focusing on is automated mobility, which can, again, alter, it can cause new design requirements on individual vehicles, alter how individuals travel, spending more time in vehicles, potentially arising from additional unloaded vehicle miles, and so on. So a large influence that these three potential topics of future mobility can have on each other, and really we feel it's important to look at these from a system perspective. Next slide. So a little bit of background on Polaris itself. What is Polaris? This was a project originally funded by the U.S. Federal Highway Administration with several core focuses. One was to look at how to model traffic control centers and ITS systems from a planning perspective, so really to have some way to estimate what are the impact that these things are having on the networks they're meant to control, and also at the same time to enhance interoperability among existing tools that Federal Highway and other research organizations had been developing in terms of travel demand modeling, traffic supply modeling, highway operations, and all the different models where typically they would focus on one aspect of this. So the Polaris core design idea was to try to integrate all these models into a unified effort to expand the reach of the modeling tools. It was designed as a general purpose set of core libraries which allow flexible model development in the agent-based modeling space. So it was meant to be modular, extensible, reusable, and most importantly, high performance due to a lot of the significant issues that are arising around runtime with some of the more advanced travel demand simulation modeling codes. So Polaris itself resolves itself into a repository of useful code and model fragments built using these core libraries focused on common transportation objects and modeling patterns. So it was designed to be open source and extensible by researchers. So everything exists on an open repository GitHub page. There's also a set of support utilities and fully designed travel demand modeling applications that come along with this. Next slide. So beyond the original focus, the use of Polaris itself has expanded significantly under the U.S. Department of Energy Smart Mobility Program, looking at, as I mentioned, some of these issues around the smart mobility analysis, with a key focus on multimodality, things like ride sharing, bike sharing, transit, and so on, connectivity and automation, urban science, decision science, really trying to understand the behavior of users within these systems, and then connection to vehicles and infrastructure, which is sort of the hook on energy. So as BEVs become more prevalent, where do they charge and how do they function and so on. Next slide. So the Polaris system itself then is a set of tools, including a network editor for generating transportation system models. So how to incorporate information from different sources and build simulation networks in a common set of I/O databases and processes in an open source, the SQLite framework. It's also a set of GitHub repositories, which can be built to run the agent-based simulation models, as well as both an interactive and a web-based post-processor. Next slide. So the long-term vision for the Polaris modeling framework is within the Department of Energy space and within others is where we have the Polaris travel demand model sitting at the center with aspects of population evolution, so long-term choices that people are making, like home, workplace, vehicle choice, continuously integrated activity demand and traffic flow simulation modeling, which feeds back into the long-term choices. And then outside, we have vehicle technology markets, land use modeling, and energy and grid modeling, which we feel can all be integrated to this travel demand modeling framework, all enabled with a baseline calibration framework and then connection to autonomy, our vehicle simulation tool for the transportation energy analysis. Next slide. So a key focus within Polaris as an agent-based model where we try to represent individual travel behavior are that changes in travel demand are one of the key sources of uncertainty that have been identified in preliminary works by a number of researchers across the national lab system in the US, where we're seeing this as basically the key driver of uncertainty in what are the future energy use estimates in the transportation system. So some of the questions we want to focus on in terms of the behavioral space are: what impact do these technologies have on travel planning and scheduling? Can these shifts be managed or induced through information provision and personal signaling? So can we share information to control how individuals make decisions? What are the impacts that ride sharing, autonomous vehicle systems, and mode shifting going to have on energy use? And then how do all of these considerations play into long-term choices such as land use and vehicle transactions? And most importantly, from our sponsor perspective, is what can DOE do to influence these decisions for energy optimality? So it's a wide-ranging project partnering with a number of other labs and universities to look at these topics. Next slide. So the way that our Polaris model functions, again, it's a set of long-term, midterm, and within-day choices made by individual agents. So the long-term choices include there's a population evolution component, but then there's a household vehicle choice and technology choice models, which are all influenced by the home and workplace choice and feedbacks from the within-day choices. There's also midterm choices in terms of routine activity patterns, so pre-planned activities, whether it's a worker, school, child, and so on. That generates constraints for the within-day choices. And the within-day choices are continuously integrated between their activity decisions and their travel decisions. So there's a continuous feedback loop between those two things. So there's a lot of effort going on in the development of the Polaris model to updating these choices at every level to represent future mobility technologies. Next slide. Now, the connection to energy comes through an integration process with our autonomy vehicle simulator. So this is an individual vehicle powertrain simulation, which is connected through the traffic flow outputs of Polaris. So so the Polaris model generates the trips for an entire day for an entire population. And those trips are then run through a stochastic speed profile generation process to basically turn the outputs of a mesoscale traffic simulation into real-world drive cycles through this Markov chain of Monte Carlo process that is then fed into our autonomy simulation model, which simulates every component of the powertrain, following a second-by-second speed trace to put both the energy use of that trip and then can be connected to economic and GHG analysis as well. Next slide. So the Polaris demand model is built from a large number of integrated statistic, heuristic, and discrete choice models, so representing the different agent behaviors. So again, after the agent initialization and long-term, so you can see moving from left to right is sort of the long-term, intermediate, and second-by-second choices that the individuals make, the individual agents make in the travel demand model, where there's an activity generation, scheduling, and planning process model run continuously throughout the day and continuously updated from the network inputs. Next slide. And the network model on the traffic simulation side is something called the simulation-based dynamic traffic assignment process, where all choices in terms of routing, in terms of route changes, are initialized, are handled at the individual agent-based level. So each agent selects its own route from a weighted A-star, time-dependent A-star, or intermodal A-star choice process, depending on the trip type. And then that path is followed or altered as the individual agent sees the network characteristics. So this is a continuous process between agent planning, activity generation, and movements through the network, which can be changed at every decision point, which is currently nodes in the network, using a bounded rationality route selection model. Next slide. So the Polaris Chicago model is Chicago is the test bed we generally run on. We have a number of other cities implemented, but Chicago is the one we spend most of the work on. So the current model is consists of a transit network, a street network, and a set of land use characteristics. So the transit network is fairly large with three main service providers, about 217,000 links in the transit network, including some walk links to connect the street to the transit trips. There's also a street network with about 31,000 links, nearly 19,000 nodes, almost 8,000 traffic signals, all of which is simulated on a total of almost 33 million trips by 10 million agents every day we simulate. And the trips occur from about 170,000 individual activity locations. So these are centroids of activity spaces where individuals travel from. So it would be basically a residential block to a school, or a residential block to a commercial block, and so on. So that's all drawn from land use databases taken from our local planning agency. Next slide. So in order to run this Polaris model, there's been significant effort in developing high-performance computing applications and calibration routines. So Polaris is designed and currently being implemented to run on cluster computing frameworks, Linux, and a large process under the DOE Department of Energy project is focused on calibration and using big data sources to calibrate these models. So a lot of effort being implemented in our using an EMU's Swift framework, which has been developed at Argonne National Lab, sort of a general process for controlling large-scale runs on HPC, has been implemented to calibrate the model using basically measured traffic data or measured demand data and so on that is feeding into the model. Next slide. And as I mentioned, a lot of effort being expended on our side in making sure this runs on high performance computing, so being implemented in a Linux environment so that it can compile. It's basically meant to be cross-platform, so runs with both Windows and Linux. And some detail there on what we're targeting in terms of the Intel Phi nodes. Do I have, how much time do I have left to present?
A few minutes. Yeah, or no problem. Just.
Sorry, I can't hear you. There we go. That's okay. Okay, I'll run through a quick case study then, sort of describing the process we did for one CAV analysis using our current model. So if you go to the next slide. So we've done some preliminary analyses on the potential impacts of a set of CAV technologies on travel demand and energy use for the Chicago area. Next slide. So from the behavioral perspective, we look at modeling changes in traveler value of travel time. So there's a thought that traveling in an autonomous vehicle reduces some energy or some burden on the driver, decreasing the value of travel time savings spent in the car. So we look in the literature. There's currently, because these things don't really exist, there's no real empirical analysis for what the potential value of travel time in a cab would be. But we drew some values from the literature and decided to study reductions in VOTT from 50% to 70% of the current auto driver costs, and then see how that filters through the behavioral models. Next slide. We have also implemented a willingness to pay, so a model for additional, what individual households would be willing to pay, marginal cost for CAV technologies. This is based on, again, because these things not generally in the market. This is largely based on a number of stated preference surveying efforts, but we take these models and develop our own model just to have a reasonable basis to distribute the CAV technologies throughout the population. And if you go to the next slide, you can see the results of implementing this. So we calibrate our simulation models, what we're getting out of the stated preference studies, and then look at the fleet penetration at different costs. So if we and again, these are all assumptions based on 2040 model runs, assuming that everyone who was willing to pay for a CAF technology would pay and have that when have that technology implemented when model is run. A strong assumption, but we see that if the marginal cost of the level 4 technology is $0, then it was assumed 100% penetration, dropping down to about 10% at $15,000. And you can see the geographic distribution based on the models that we've pulled from the survey data over the Chicago region on the lower right-hand side, where not much penetration in both close-lying and low-income areas, with much higher penetration in outlying areas where more travel is done. Next slide. We've also updated our traffic flow model that has been implemented in the Polaris Network Simulator to modify on the fly the link capacities based on the current penetration level of the CACC equipped vehicles in the link. So this has been done based on a large number of microsimulation studies, as well as some field efforts to simulate the change in capacity for a single link. So this is continuously tracked as the model runs, where we, on a 6-second by 6-second basis, we know the number of CACC enabled vehicles within each link. So we modify for each time step the current capacity. So we can, if more CACC vehicles are on a link, we get more flow through that link. Next slide. So the deployment for the scenarios we ran includes varying the marginal AV costs crossed with the value of travel time savings change to generate our 9 cases that we run. And then we evaluate this using our Chicago model, which is, again, 10 million travelers, about 28 million trips. Next slide. So focusing on mobility impacts, we see that travelers with access to CAV technology take longer trips as expected. Again, as the driving impedance is reduced, people tend to consume more of that more driving time. So we see that the 11.8 mile baseline average trip length increases to almost over 17 miles at the highest CAV penetration levels, and that the longer trips as because the reduced burden of driving. Although we do see some congestion increase as well, as travel time increases 7% faster than the travel distance. So there's some rebound effect in terms of the increasing the capacity also increases the travel demand as well. Next slide. Now, also through the connection of our autonomy model, we look at the potential energy use impacts of this, and we see, again, in the worst case, there's a potential 45% increase in fuel use. Although the efficiency does increase slightly, we would expect that as people are traveling more, as VMT increases, that the fuel use would also increase. Next slide. And then we can look at those results geographically to see where, comparing cases and looking at where the increased travel is happening. So we see when we're comparing, when we hold the value of travel time change fixed and look at zero marginal cost versus a high marginal cost case, we see that there is much more fuel consumed in, again, the outlying areas where people are more likely to buy these vehicles and where people are more likely to have longer commutes. Again, because that's largely the population that these vehicles are beneficial for. In the right side, and we see a more uniform impact when it's just a value of travel time change. Next slide. So in summary, we've combined the analysis of CAV energy impacts across multiple dimensions simultaneously, including travel behavior, network operations, and vehicle technologies, really to look at the Department of Energy technology programs and their impacts under potential future mobility scenarios. So we've generated this regional transportation energy estimation tool, which allows us to analyze the intersection between transport policy and vehicle technology, and just demonstrate this through our case study on CAV's analysis. Next slide. Let's just move to can you move to slide 29? So just to say that, we have a Chicago case, but there's also multiple additional use cases we are running in Polaris currently. So there's an Atlanta model that's been developed with a Georgia Tech Research Institute. There's also a Beijing model being developed at Tsinghua University, University of Michigan working on an Ann Arbor model and a Detroit model, and we're developing one sort of large-scale model for Illinois statewide long-distance travel demand model. Last slide. So thank you for your attention, and again, sorry for the technical difficulties. And say for more information, you can visit us on our website at polarisus.anl.gov, or check out our repositories. So everything is open source that we've developed, and it's all on GitHub. All right, thank you.
Do we have questions from the audience? Madhav?
George, this is Madhav Marathi from Virginia Tech. Interesting presentation. What I wanted to ask you is, you folks had a license for Transims and you were maintaining it as well. So can you tell me a little bit more about how Transims and Polaris differ?
Can you repeat the question for me, Sarah? I didn't quite.
Yeah, we'll just ask the speakers to come here.
Okay.
Questions and to directly.
Hi, Josh. This is Madhav Marathi from Virginia Tech.
Hi, Madhav.
Hi. I know that you folks are also maintaining Transims, something that we had developed when we were at Los Alamos, and Chris is here as well. So I want to understand what the differences between Polaris and Transims were. At least in the presentation, I couldn't get to understand it.
Okay, yeah, so we had been supporting the Transims deployment efforts for a number of years. The elements that made it into the Polaris model are largely the I/O, so it operates on a very similar network structure. Similar data tables feed into the model. The implementation is quite different than Transim, so everything here is implemented as a single process. So it's a single application. It's not a set of different applications as Transims is implemented, where you would run sort of population generation, would generate a population, and then the demand model would set the activities, and then the network router model would run to route all the activities. I mean, you know how Transims works. In here, all of those steps are implemented as behavioral functions within a single software agent. And it looks like the screen is frozen. Okay, so everything is handled as different function calls from a single software agent. So as the agent plans its day, schedules its day, moves through the network, it persists as a single object. It's not split up into different processes. Does that sort of address what you were?
Yeah, we can talk again later on too. I'm taking time from the session, but yes, thanks.
Okay.
Thank you very much. We have to come to a close with this session, but I will also get back in touch because I'm very interested in especially in the calibration work you were talking about. So thanks again, and we'll continue via email. Bye-bye.
Thank you. Bye.